Good evening. In Chapter 1, we realized that the Earth is facing a grave crisis due to the fact of human overpopulation, and that human overpopulation is both consuming the world's resources as well as polluting the resources that we already have, and that the only way that we're going to survive as a species is if we either control our rate of population increase and or we do something about making sure the world's resources are sufficient to feed the number of people that we have. In Chapter 3, we looked at the way in which the world produces those resources through a system we called the ecosystem. And we learned a little bit about how that ecosystem functions and what it does to provide and recycle the necessary resources to components to make the resources to keep the human population alive. In Chapter 4, we're going to look at how ecosystems evolve. One of the things that we learned in Chapter 3 was that ecosystems are incredibly complex systems that comprise of both living and non-living things, and that they interact with each other in very specific ways that help to support each other and that help to keep this ecosystem going. However, over the many millions of years in which these ecosystems have existed, it's been necessary for them to evolve from time to time to accommodate the introduction of new species or to accommodate changes in the environment. In Chapter 4, we're going to look at some of the mechanisms by which ecosystems respond and evolve to changes in the world so that they can continue to be the sustainable producers of the things that we need to stay alive. Chapter 4 begins with a study of the dynamics of natural populations. What this involves is an understanding of the way in which different species within a given ecosystem interact with each other. Normally, if there were no other factors involved, we would expect that the population of a given species would continue to grow over time in pretty much of a linear fashion. Obviously, the more time, the more number of individuals that are being produced. However, this is not what actually happens in an ecosystem. Instead of a straight line population growth increase, what you get is something that's more S-shaped, like this red line here. That is, the population starts out at a relatively low level, then reaches at a point at which its population numbers begin to increase rather dramatically. But eventually, the rate of increase levels off at some sustainable number of individuals. The point at which they level off we call the carrying capacity of the ecosystem for that given species. And as long as the number of individuals stay at or below the carrying capacity of the ecosystem, all of the individuals will survive. On the other hand, we sometimes see population growth curves that look more like this blue line. As you can see, again, it starts at a relatively low level and then begins to increase. But unlike the S curve, in what we now call a J curve, the number of individuals continues to increase well beyond the carrying capacity of the ecosystem. When that happens, like occurred on Easter Island, the number of individuals in the ecosystem is greater than the ability of that ecosystem to support them. And if that continues to go on, the whole individual species can collapse due to a lack of resources. This J curve, as you may have seen already, is similar to the population growth curve of human beings today. What we need to find out in Chapter 4, and what we will see in Chapter 4, is how species learn to interact with each other so as to stay below the carrying capacity, and also to see what happens when those numbers of individuals exceed the carrying capacity. So, how do ecosystems put limits on population? As we'll see, ecosystems set the population density of any given species within that ecosystem based on two competing factors. One is called biotic potential, which is how well does the species produce offspring, and the other is environmental resistance, which determines how many of those individuals will live and grow and survive to produce new individuals within that ecosystem. We'll see that species develop different strategies for dealing with biotic potential. Some species tend to have many offspring in anticipation that many of them will die, but at least some of them will live. Whereas other species only have a few offspring, but they nurture them to make sure that they survive into adulthood so that they can continue the species population. Counteracting this biotic potential are things that we call environmental resistance. Environmental resistance often deals with conditions and resources within an ecosystem to help support that particular species. Things such as the amount of food or nutrients that are available for the species, availability of drinkable water, availability of suitable habitat, the presence of predators, and in particular, disease. All of these things represent a resistance to the increase in growth of a given species. And we'll see that the actual number then of a species within an ecosystem is the net result of its ability to produce offspring versus the ability of the environment to counteract that amount of individuals. If either one of these two factors gets out of kilter, either you'll have too great a population, as we saw with the J curve, or you may have the extinction of a population, as we saw also in the case of a J curve. Getting the right balance, one which keeps the species number at or below the critical number, is important then for the continuation of a species within an ecosystem. While environmental resistance may often be the result of conditions in an ecosystem, such as the temperature, whether it's too hot or too cold, or the amount of precipitation in order to support a given species, more often than not, the limiting factor within an ecosystem involves the interaction of various living species within that community. We will in this chapter explore the concept of symbiosis, that is, how do different species interact with each other in such a way as to either support each other or to compete with each other. We'll see a couple of interesting case studies in which different species compete with each other. For instance, the story of the moose on Isle Royale and their competition with a pack of wolves that serve to limit their population. As the population of the moose increases, the population of the wolves increased based on the increasing amount of food that those moose became. On the other hand, when disease set in and reduced the number of wolves, then the population of the moose began to increase. And there was a dynamic interaction between those two populations. We'll also see that some species develop unique strategies for avoiding competition by either a process called resource partitioning, that is, by finding resources that they don't have to compete with, or by finding niches within a habitat in which they are the only species to occupy the niche, and therefore the only species that feeds on those particular resources. And then we'll finally look at a very interesting phenomenon called a keystone species. Keystone species is one which is so critical to the functioning of the ecosystem that if it's removed from that ecosystem, the entire ecosystem will collapse. One of the examples given is that of the starfish that are shown in the accompanying photograph. These starfish feed on a type of mussel or clam that inhabits their ecosystem. And if the starfish weren't there to feed on those clams and remove them on a regular basis, the clams would grow and multiply beyond numbers and overwhelm the entire ecosystem and consume all of its resources to the detriment and eventual elimination of all other species within that ecosystem. So having a predator such as the starfish there to remove them and limit their population is critical for all other individuals within that species, in that ecosystem, to survive. So then, what environmental resistance factors ultimately determine what species will live or die within a given ecosystem. This is the concept enshrined in Darwin's theory of evolution, and it is summed up by the concept of natural selection. The concept of natural selection says that a species that has an advantage over other species for either getting food or surviving predators is more likely to survive and pass on to the next generation of its species those characteristics which gave it that advantage. In Darwin's case, he came up with this idea by looking at a population of finches in the Galapagos Islands. And what he determined is that these finches had different characteristics based on the different kinds of food that they ate. For instance, finches with very strong, heavy beaks were birds that fed on nuts and berries and other perhaps hard to crack food sources, whereas finches that had very narrow beaks were ones that fed on insects and used the advantage of the narrow beak in order to burrow into holes in trees or bushes or the ground in order to pull out the food that they ate. So on those islands where the primary food source was basically nuts and berries and types of foods that needed to be crushed, the birds with the heavy beak survived because they could obtain the food source more readily and more easily than those birds with the narrow beak. On the other hand, on those islands where the primary food source were insects, those birds that had the narrow beaks and therefore could more readily access those insects, burrowing insects, were the ones that were able to survive and compete. So natural selection then determined, that is, the environment in which the species lived through the process of natural selection, determined what characteristics favored the survival of that species. And because they were the only ones that survived, they were the only ones that were able to pass on those characteristics to future generations through the process we now know as evolution. Finally, we're going to look at what happens when species are introduced into an ecosystem from which they did not naturally evolve. Because these species were not subjected to the pressures of natural selection and evolution, sometimes they have an unfair advantage over other species within that ecosystem for competing for food and resources. And when this happens, these new invasive species can totally decimate an ecosystem. One of the examples that we'll see is what happens when rabbits were introduced into the island continent of Australia. Because rabbits did not naturally evolve in Australia, they had no natural predators. And as a result, the rabbits, as rabbits will do, overpopulated and escaped from their confinement and eventually overran Australia, and in so doing ate all the foliage, the grass, shrubs, and other food sources for many of the other grazing animals that existed on the island, so that there was no pasture, if you will, for cows and horses and other herbivores. They literally stripped the land right down to the ground. In the accompanying pictures to my narrative, we see a similar fate that occurred on a much smaller island and what the island looked like after the rabbits were through with it. As you can see, the very little green area, and it's almost all brown soil that, as happened in the case of Easter Island, is subject to erosion. However, because this happened in more modern times, humans were able to come in and eradicate the rabbits from this island, and in so doing allowed the foliage to reestablish itself, as you can see in the lower picture, and dramatically illustrates how man, if you understand the science behind a given environmental threat, how one can perhaps not only stop but reverse that environmental threat.